Welcome to this module on data transformation and cleaning. We'll start off by going through some essential data cleaning techniques in PySpark. Before we dive into our notebook, let's go over some common data cleaning examples. First one I have here is removing duplicates. We also have handling null values, as well as fixing wrong data types. These are some data cleaning examples you might run into. So let's go over into our notebook to see how we can tackle these issues. As I usually do, I went ahead and ran the first column, which has all the different libraries that we're going to be using for this notebook. So first thing I did here is load our data set that we're going to be using. And what we're going to do is identify what exactly needs cleaning in this data. So you can see the schema for the message data. Let's go ahead and display the data. All right, this is what the data looks like. It might not make too much sense for you now, but later on, as we explore the data even more, we're going to be coming back to this cell to verify what it currently looks like versus the changes that we're going to make it look a little different. So the first thing I'm going to do is check for nulls. So that means we're going to be checking to see what missing data we have in this data set. But before we do that, it's always good to get the amount of records that we have in this data set so we can compare all the other columns to what the total amount of records should be. So you can see the total amount of records is 52,500. So let's go ahead and check for nulls. All right. And what this is doing is selecting into the messy data frame and getting a count of how many records is null using the isNull function as you see here. And what we're able to do here is go through the columns and see the amount of missing data that we have for each column. So you can see here, event ID is missing some data, as well as user ID, content ID, timestamp. And what it does is shows us the amount of missing data that we have in each one of these columns. If I scroll to the right, error type has 47,000 data that's missing. And it looks like that's the last column that has missing data. So just to make this a bit more real, let's go back up to the data set. And I'm going to scroll down to error type. Just with the naked eye, we could just see that there are a significant amount of nulls in this column. Just scrolling down, you see there's a lot of nulls. 47,000 is going to be a lot easier to spot that out compared to the other columns that we saw earlier. All right, so that's how we're able to do a little bit of spot check. That's not necessary, but I like to do that just in a case where you have 47,000 out of 52,000 of the data being null. It's going to be quite easy to spot that just by looking through the data. All right, let's move on to check out for duplicates. So to check for duplicates, what we do is just use the data frame and put the drop duplicates function and get a count on how much of that data that we have. So let's go ahead and do that. And there we go. We have 2,500 duplicate records inside of this data. So moving on to seeing some data type issues, the column that we're going to be focused on here is duration underscore seconds. And duration underscore seconds, just from the name, you can understand that this should be an integer because seconds will be in numbers. And since we printed out the schema earlier, let's go ahead and see what the data type is for duration underscore seconds. I'm going to scroll back up to where we printed out the schema. And you can see duration underscore seconds is a string. So just to spot check and make sure that is actually supposed to be numbers, let's go ahead and print out the data for that column. And just as I assumed, duration underscore seconds gives us numbers. So this can easily be an integer instead of a string. All right, we've now seen some of the common data cleaning examples and how we've been able to use PySpark to find out these issues within our data set. So now let's go ahead and see how we can clean them. Starting with removing duplicates, we already saw that the drop duplicates function is a way to do this. And what we could do now is save anything that we're working on moving forward to clean underscore data frame. So we're going to make sure that anything that we save to this data frame is clean data that we can use. So let's go ahead and drop those duplicates. All right, we've dropped the duplicates, and now we have a count of what the data is now without the duplicates. And this makes sense because remember, the total data we had for the messy data was 52,500, and we had 2,500 duplicates. And once we remove that, we now have 50,000 records within this clean data frame. Moving on to handling nulls. What we're doing here is using the .NA fill to handle wherever we find missing data for the column error underscore type. Remember, this was the one that had a substantial amount of missing data. So if the error type is missing, we could just say it's none in this scenario. There is no hard and fast rule on how you handle nulls. The goal is just to understand how exactly you want to handle them for your use case. The next piece I have in handling nulls is for the columns user ID, content ID, and event ID. So for these key ID columns, if we don't have the event ID, then the data isn't useful. So we're going to go ahead and drop them. And I also included the timestamp column here as well. We also have some data in there that come in as null. So once we've identified all the columns that we want to clean up, we can go ahead and then use the drop NA function and save that to our clean data frame that we're working on. And once we've done that, we'll get a count of the records we now have in this data frame. All right, we went from 50,000 to 40,778. So let's move on to fixing data types. Remember, we identified duration underscore seconds as a string. We now want to change it to an integer. To do that, all you have to do is do a .cast and specify what the new data type should be. And once I've done that, I'll print out what the new schema should look like. All right, there we go. We have duration seconds now showing up as an integer. So moving further down, what we could do now is verify that our data is clean by making sure that the nulls that we had earlier have been removed. And there we go. You can see we no longer have any columns that showing up as null. So that means the cleaning that we did earlier worked. And now we can take a look at what the data looks like inside of this data frame. And just to spot check our column that had multiple nulls, which was error underscore type, we can see we've changed everything to none instead of having it show up as null. So this is an example of how you can use these data cleaning techniques within PySpark to make sure your data is clean in the way that best suits you to move forward with your data set. And of course, once you're done, you can go ahead and save this out, just like I have here. In this clip, we're going to explore how to transform data in PySpark using joins and aggregations. And we're doing this because these are critical operations for any ETL pipeline. So first, I'm going to import the necessary libraries we're going to use for this notebook. Now let's go ahead and load our 3 data sets that we're going to be using. The first is streaming events, and the other 2 are reference data sets, which are users and content catalog. So let me go ahead and run this. All right, you can see each of these has been loaded to a data frame. Now let's go ahead and look at the schema. All right, so now we have the schema for each one of these data sets. Starting with event schema, you can see I have user ID. And when I scroll down to user schema, I also have user ID. We know we can definitely join these 2 data sets using user ID. Now going back to event schema, we also have content ID. And when we scroll all the way down to content schema also has content ID. So now we see user ID and content ID are going to be our join keys, which we can use to join these data sets together. Now let's go ahead and perform our first join to enrich the events with user information. So this is the syntax that PySpark uses to create a join. And this is an inner join, which means we're only keeping events where the user exists in our data sets. So I'll go ahead and run this. And further down in this cell, you can see that we're also checking to see how many events we have before and after the join. We'll talk about that in a second. All right, now we have the results for the join. And at the bottom, you can see the amount of records we have before the join and the amount of records we have after the join. And it's pretty clear that we've lost some events. And that's expected because of the type of join that we just did. If we want to keep all events, we should use a left join instead. So let's go ahead and do that in the next cell. So you can see we're doing a left join here on events and user data. And further down, we're taking the result from that and performing a left join on content data. And once we've done both of that, we'll just display the results. So let me go ahead and run this. All right, there we go. We now have a fully enriched data, which has all 3 data sets that we're working with. You can see we have event ID, user ID, as well as content ID. And if you scroll to the right, you can see more details like the title and genre. So now that the events data is fully enriched, let's move on to some aggregations. And this is going to allow us to summarize our data. And first, let's go ahead and get a count of events by subscription tier. And we're able to do this by doing a group by on subscription tier and an order by on event counts in the descending order. And of course, a tally on the count of event counts that we have. So let me go ahead and run this. All right, there we go. These are the type of things that you can do with an enriched data. Next, we can also analyze the streaming duration by genre. You can see how we do this over here. So let's go ahead and get the results from this. And there we go. We're able to group the genres together and get the average streaming duration for each one of them. For more complex analysis, we can compute multiple aggregations in a single query. A good example of this is by analyzing the content performance by subscription tier and genre. I have the query over here, and let's go ahead and see the results from this. And there we go. This gives us a comprehensive view of how genres perform across subscriptions. And of course, now that we have all of this, we can now save this enriched data set for downstream analytics. So let me go ahead and do that. And there we go. Our enriched data has been saved. And that's how we can use joins and aggregations to transform our data in PySpark. Doing all this allows us to enrich and summarize our data and makes it better prepared for loading it into target systems. In this clip, we're going to go through how to use user-defined functions in PySpark. UDFs, or user-defined functions, allows us to extend PySpark's functionality by writing custom Python functions that can be applied to data frame columns. Let's get started by loading our data and seeing how UDF works. All right, there we go. Now you can see we have our streaming events data loaded. Let's go ahead to the next cell where we're going to create our user-defined function. And in this simple UDF we're going to create, we're going to calculate streaming quality score. So let's go ahead and run this. And of course, you have access to view the cell in its entirety by accessing this notebook within your exercise files. Keep that in mind as we create some other functions within this notebook. All right, there we go. You can see now we've been able to use the user-defined function to retrieve the streaming score. So moving on to the next cell, what we're going to do now is view the execution plan of the data frame by running the explain function, which will let us know how efficient this UDF was. And here we go. So looking at this execution plan, what this tells us is that the UDF is using something called a batch eval Python, meaning it's using a Python UDF, which shows that Spark is calling Python row by row, which prevents vectorized operations that can process multiple values at once. This is quite inefficient. A better option is using vectorized UDFs. In the next cell, I have a vectorized UDF option here, and I'm going to be running the same logic as I used with the previous UDF, but instead of one value in each row at a time, this vectorized UDF is operating on the entire series at once. So let's go ahead and run this. And in the next cell, we'll also use the explain function to get more details on how this worked. All right, we have the results. And let's go ahead and run the next cell that gives us the explanation of the vectorized UDF. And you can see that the execution plan from the explain function shows that the plan is using an arrow eval Python operation, as opposed to what we saw previously, which is the batch eval Python approach for the regular UDF. Now, to make this more pragmatic, in the next cell, I have a script that allows us to run both of these UDFs and compare the results. So let's go ahead into the next cell and run that. So based on this, you can see that the results between the regular UDF versus the vectorized UDF is quite significant. You can see that using the vectorized UDF is 3.9 times faster than using the regular UDF. And it's important to note that while UDF is a common topic in PySpark, when using Databricks, it's recommended to use functions that leverages Databricks' high-performance query engine, which is known as Photon. And this goes beyond the topic of just PySpark. so feel free to research that for more details. Building efficient ETL pipelines requires applying key optimization techniques. Let's take a look at 3 critical optimizations. To set this up, let's load in our data first. All right, there we go. You can see we now have 2 data frames, one called DF and the other called users DF. The first optimization we're going to look at here is broadcast join. So joins are one of the most expensive operations in Spark ETL pipelines because they usually involve shuffling data. And this requires network transfer and disk I/O. In this cell, we're going to look at what running a join that results in shuffled data looks like. And we'll do this by taking a closer look by running the explain function within the cell. So let's go ahead and run this. You can see here we have the execution plan. So to look at the execution plan a bit closer, let's go ahead and start from the top. And looking at this plan, the way you know shuffling has occurred as a result of this join is when you see something called exchange. And we can see exchange over here. And if I scroll down to more details on the exchange section, we're also going to see something called hash partitioning. And what this is going to do is redistribute the data across the cluster. So how do we avoid such an expensive operation? We do this by using broadcast joins. In this next cell, you get to see an option of how we run this using broadcast joins. You can see that I include the broadcast function inside of the join. So let's go ahead and run the cell and review the execution plan. So scrolling to the top of this execution plan, you notice that it's using a broadcast hash join operation instead of what we saw earlier inside of the regular join. This broadcast join is more efficient because the entire user's data frame is copied to every executor, and this eliminates the need to shuffle data during the join. And to emphasize the difference between both joins, in the next cell, let's go ahead and do a comparison between the regular join and the broadcast join. So let's go ahead and run the cell. And you can see that the broadcast join is 2.7 times faster than the regular join. This is a significant performance boost. Keep in mind that Databricks' offering of Spark automatically enables broadcast in its engine. And when I ran the regular join earlier, I had to manually disable it just so you can see the difference and the benefit of having it enabled in the following cell. The next option we're going to look at here is caching. When you use the same data frame multiple times, caching can dramatically improve performance. In this cell, I have an example of a data frame without caching, and further down you see an example with caching, and we compare both of these just to see how they perform. So let's go ahead and run the cell. There we go. You can see the non-caching took about 2.6 seconds, whereas the cached options took 1.05 seconds. You can see that's quite a difference between both of these. And with the larger data set, you could definitely see some performance boost between using cached versus non-cached. So moving on to our next optimization option, we're going to talk about partition rights. Partitioning your data is crucial for downstream query performance. And what partitioning does is it creates a directory structure that makes it easier to retrieve data. And it does this in such a way that when you're querying with the filter on partition column, Spark skips reading the irrelevant partitions entirely. This is known as partition pruning. So in this cell, you can see that I'm specifying the output path where the data is going to be partitioned to. And I also select which column within my data I want this to be partitioned by. This is specific to this data set, but a best practice around this is to partition by columns that are frequently used in filters. So device types makes a good candidate for this. So let me go ahead and run this cell to see what this looks like. All right, here we go. And one thing you see here is that when we scroll all the way to the right, we have folders that are named by the device types that we have here, like mobile, TV, tablet, and devices. So now when data is filtered by TV, There's no need to go into the other partitions that have nothing to do with TV. This means that you're able to get the data that you need a lot more quickly. Overall, partitioning is a very good technique to use. You just want to make sure you avoid over partitioning, which means having too many small files, as this can then become inefficient. Welcome to this module on loading data efficiently. We're going to start by writing data to various destinations. So over here in my Databricks environment, I have this notebook that shows how we can write data to various destinations. I have many different destinations that I show here, and you can see them over here. I have Parquet format, ORC format, Delta Lake format. I also show you how you can partition data. And since most of these formats have been covered in previous clips in this course, I'm going to skip over them. But as always, you have access to the notebooks where you can see for yourself and also practice. And further down, I also talk about how you can write data to a database table. So these are external tables that you might use. In this case, we're going to use Azure SQL Database. So that's actually where we're going to start using this notebook. Let's go ahead and set up our PySpark environment as well as import the data sets we're going to be using for this notebook. All right, we've been able to successfully load in our streaming data that we're going to use for this notebook. And just to get a sense as to how much data we have here, we're going to run this. And this shows us we have 50,000 records within here. And I'm going to scroll all the way down through these formats that we're skipping over and going straight to right into the database. And to connect to the database, I'm going to be using the database connection parameters here via Databricks widgets. So I'll go ahead and run these widgets. And you can see it gives me the different parameters that I'm going to use here. I already have the database name that I want to connect to. I just need to put in my server details and my password, as well as the table name and my user credentials. I'm going to go ahead and do all this. And once I'm done, I will remove my widgets so you guys don't see my credentials. And we'll carry on once that's done. All right. You can see that my credentials have been ran and I have removed my widgets. So I'll move on to go ahead and make sure that we can connect to that database. Let's go ahead and run this. And there we go. I have made connection to that database. And in this next cell, you see that as we write to this database, we are putting some optimization techniques that allow us to write in a much more efficient way. For this example, we're only working with 50,000 rows, but imagine if you were working with 1 million rows or more. These techniques that we're talking about here would definitely come in a lot more handy in that situation. So first off, you see here that we have the data partition, which means that the data is going to be partitioned to 12,500 rows per partition, which balances parallelism without creating too much overhead. You can see further down, we have a batch size, which is set to 5,000. And doing this means that we'll send 10 total batches across all partitions. Again, very small data set, wouldn't be too significant, but in a larger data set, this is going to reduce the network round trips while keeping memory requirements reasonable. And the last piece you see on here is I have the transaction isolation level set, and I have this set to read committed. This provides a good balance between consistency and performance, and using read committed prevents dirty reads. And this is when you are reading uncommitted data that might be rolled back in the future. So these are all different optimization techniques that we have as we write data to this specific location. Some of them, like the isolation level, is unique to when you're working with transactional databases, but all the others are good best practices to leverage as you write data using PySpark. So let's go ahead and run this. All right, there we go. Our data has been successfully written with all these optimization techniques that we included. So let's move on to our next topic here. And this topic is called Z-ordering. Z-ordering is an optimization technique that can be very useful when writing to Delta tables. And what it does is it physically reorganizes the data to co-locate related information based on specified columns. And you can get the most out of Z-ordering when you're working with very large data sets. For this example over here, I'm only working with 100,000 rows. And even with that, we'll still be able to see some effects of using Z-ordering. So let me go ahead and pull in this data set. There's our 100,000 rows that we're working with. And next, what I'm going to do is create an unoptimized Delta table without Z-ordering and an optimized delta table with Z ordering. You can see here that I'm setting this Z order on these two columns, user ID and content ID. And this is how Z ordering works. If you're frequently running queries that are filtered by certain columns, Z ordering will help Data Lake skip reading irrelevant data files that aren't needed for those columns. This is going to help you retrieve data efficiently. And there we go. We've been able to create the unoptimized delta table as well as create the Z ordering delta table. So in this next cell, what I'm going to do is compare both of these to see what performance benefits we get from using Z ordering. So let's go ahead and run this. You can see the amount of time it takes for us to get the same amount of rows from both of these tables. And from this, we have a 35% increase from using Z ordering, which turns out to be 1.5x faster than using the regular unoptimized delta table. And like I said before, you get even better performance improvement the larger the data set is. Incremental updates are essential for production PySpark ETL pipelines. It allows us to process only new or changed data rather than reprocessing everything. Let's go ahead into the notebook to see how this works. In this notebook, I'll go over 3 approaches you can use when implementing incremental updates using PySpark. The first one I'm going to go through is append, the second is merge, and the third is schema evolution. And before we begin, I'm going to go ahead and import the libraries for this notebook, as well as the dataset we're going to be using. For this demo, I created a sample dataset, and I also defined the schema. So I'll go ahead and run this so you can see what the data looks like. It's also important to highlight here that I'm writing this to a delta table. While this is the format that I choose to save this to, you can save this to Parquet, CSV, or any format that you choose to have your data saved as. All right, there we go. You can see that we now have a data frame that shows the existing data. And if you scroll further down, you can see the schema as well as what the data looks like. As you can see, we only have 5 records in this data frame. And this is the data we're going to be using throughout this notebook. So let's go ahead and start on the first approach here, append. For this, I'm going to take 2 existing records and modify their IDs. And once I've done that, I'll go ahead and append that to the delta table. And this means I'm going to add the 2 new records to the existing data set. Let's go ahead and run this to view the newly appended data. All right, we can now see the newly appended data. And this is apparent by looking at the event ID column. And I modified it to show it as append underscore the ID details. And if you look further down, when I run this next cell, this will show us what the data looks like in totality. So you see we have the 5 records and the 2 newly appended records. And this is how you use the append approach to incrementally add data using PySpark. So moving on to the next cell, we could talk about what the merge approach looks like. You can see here, we start by getting a record to update, and we also get a record to insert. For the update section, what we're doing here is modifying 2 columns, and that's the duration section as well as the quality section. So when we run this, we're going to be looking out to see that those have been correctly updated. And for the merge operation, we're going to be having a new record, and this is going to be clearly stated as a new record called merge new record in the event ID section. So those are the changes that make up this upsert in this merge operation. Another thing to point out here is how we're leveraging PySpark to perform this merge operation. So scrolling further down here, you see that we're leveraging PySpark's when match function to check each record in the incremental data frame. And this allows us to check if a record within the same event ID already exists in the target location. And if it does, we'll go ahead and update it. And if not, we'll insert the new record. So let's go ahead and run this to see how this works. All right, you can see the records that have come out of this merge operation. The first we have is the event ID that has been modified. And to see this, let's go ahead and scroll to the right to see if the information that we expect is there. So you see when we scroll over to the duration section, the data there has been modified to 9,999. And moving further into the quality section, you can see the quality section has been modified to show as Super HD. So those are the expected changes we are looking for the update section of this. Now looking at the merge section of this, the second record under event ID shows that this is a new record that has been added to this data set. And we can see that when we open this up, this event ID column clearly shows the second record as a merged new record. So scrolling down into the next cell, let's see what the data looks like in the Delta table. All right, there we go. We can see we have 6 records, and that makes sense because we know one record was inserted here, which is this record in the 3rd row. And we know one record was modified here, which is the 4th one. And we know that by looking at the duration seconds as well as the quality section, which we can see over here. Now let's move on to the next approach, and that's schema evolution. And we'll go ahead and reset the schema because we're going to be using that as a point of reference as we talk about the schema evolution. All right, there we go. This is what the schema looks like now. And like I said, we're going to come back to see what this looks like once the schema evolves. And in the next cell, we're going to go ahead and create a new column. And that column is going to be called user rating. And in this column, we're going to add 2 new data sets. And for the user ratings for those columns, we're going to have them shown as 4.5. So this is an example of a schema evolution. So let's go ahead and see what this looks like. All right, now the 2 records have been added. And as a result of that, a new schema has been created. You can see at the bottom here, we now have the user rating column, which is different from what we had previously, which didn't have the user rating column. So let's go ahead and see what the data looks like now with the new data that's been added. You can see here, these are the 2 records that have been added. And this is highlighted here by looking at the event ID. And we can also see this by scrolling all the way to the right. Under user rating, we can see we have a user rating of 4.5 for both of those new records. Now let's go ahead and see how this looks like in the entire table. All right. You can see here we have 7 records. And in those records, you can see the 2 new records that have been added from the evolution of the schema. And when I scroll all the way to the right, on the user rating, the 2 new records that have been added have a user rating of 4.5, while the others are showing up as null. And that makes sense because those records existed before the user rating column was created. This module on automating and orchestrating ETL pipelines. We're going to start by exploring how to schedule our PySpark ETL pipelines. Well, there are several orchestration tools available to use. We have tools like Airflow, Dagster, Prefect, as well as Databricks workflows, which is the one that we're going to be using in this clip. In my Databricks workspace, I'm going to be focusing on automating a daily video streaming data processing workflow. And in this notebook, I start by importing the necessary libraries, as well as defining the paths that are needed. But the heart of this notebook is over here in the user-defined function, which takes in the parameter to extract the video streaming events for a specific day. And that parameter is execution_date. Once the data has been extracted, this function then performs ETL operations like cleaning and transforming the data, as well as calculating metrics by device types, country, content, and hour. And once that's done, it then loads the process data into partition columns. Now that we have an understanding of what this notebook does, let's go ahead into our Databricks workflow, which will show us how this job is scheduled. To do that, I'll hover over here and go into workflows. You can see that I've ran this a few times already. And over in the top here, I can click on tasks. And you can see I have one task, which is connected to the notebook that you saw earlier. Scroll further down, you can see I've selected a cluster so this job runs. And you can also see I specify the execution_date parameter, which is needed for the user-defined function to run. In this case, my dataset has specific dates, so I specify one of those dates. In a real-life scenario where data comes in daily, you could set the execution date to be the current date the pipeline runs. All right, now to the part that makes this automated. On the right-hand side, I can scroll down to schedules and triggers, and you can see that I have this scheduled to run every day. I can edit trigger, and this is where you can see I have the option to specify a trigger type. And the options you have here is scheduled, file arrival, or continuous. In this case, we chose scheduled. For your scheduling type, you can either use a simple approach or you can select the advanced option, which allows you to use the cron syntax. In this case, I've paused this job, so if I switch it to active, I have the option to change some of these settings. I hope you now have an understanding of how you can schedule PySpark ETL pipelines. Let's see how we can ensure we're building resilient pipelines in PySpark. In my Databricks environment, I have a notebook on this where we will go over 3 approaches that will ensure you're building resilient pipelines. The first approach is going to be using checkpoints for recovery. The second is error handling, and the last is using atomic writes. So let's go ahead and get started. We'll start by importing the required libraries as well as defining the paths that we're going to be using for this notebook. All right, now that that's done, let's go ahead and move on to checkpoints. So how does checkpoint work? Well, as you've probably gathered by the name, it gives us a reference point by saving intermediate states of our data. This allows us to recover without having to start from scratch. So let me go ahead and load our source data and show a sample of this data. And you can see that this is the video streaming dataset that we're using in this course. Next, we'll go ahead and perform some transformations. And some of them include filtering long videos and creating derived columns from them. And you can see that over here, we are explicitly saving this state to a checkpoint file. So let's go ahead and run this. All right, the checkpoint file has been saved. Now we can see what this looks like over here. And this is how the checkpoint files are saved into the step 1 folder that we specified. In a real world scenario, if a failure occurred after this point, we would pick back up from this checkpoint. As you can see, when I run this cell, we can reload the data from our checkpoint and continue processing. And there we go. This is what this process will look like. This technique is especially valuable for lengthy pipelines with expensive transformation. Feel free to run this next cell to see another example of this. Keep in mind, we're going to be using this step 2 data frame further down in this notebook. So let's move on to error handling. We know in the real world, data is often messy, and this is where handling problematic data comes in. I'll start by creating a data frame where we will load the data into. So let me go ahead and run this. All right, you can see we have some issues with this data set. We can see we have duration values that aren't proper numbers. And for the timestamp, if we scroll down, you see we have some null values. So instead of letting these problems crash our pipelines, we can implement a defensive transformation approach. So in the next cell, we'll do this by making sure that the invalid durations are set to 0. And we'll also tackle the missing timestamps by setting it to a default value. Now, when we run this, we'll see that these columns will no longer be a problem in our pipeline. And there we go. This is a much better data set that we can work with to avoid some problems. So moving on to atomic writes. What this does is it ensures consistency within the outputs for the end users of the data. And we'll do this by first writing out our process data to a temporary location. And there we go. The data has been written to this temporary location. And then the next cell, we're going to leverage this to allow us to verify the outputs before committing it. And we'll then check that all the records are present and valid. And with this process, the data will be allowed to be written to the final location only after the verification process has been passed. Obviously, this is a pretty simple example, but in a real scenario, you can write a robust if-then statement to include an accurate verification check. In this clip, we're going to be killing 2 birds with 1 stone by exploring real-time ETL pipelines while simultaneously demonstrating how to effectively monitor ETL processes. So real-time streaming provides the perfect context for discussing monitoring because streaming pipelines have unique observability challenges that make monitoring absolutely critical. So let's dive into it over here in this notebook. So I'm going to start by making sure we have our necessary libraries. And in the next cell, we're also going to define the schema that we're going to be using such that the streaming pipeline understands what data is expected before it arrives. So let me go ahead and run these first 2 cells. All right, there we go. Now moving on to the next cell, we're going to go ahead and initialize our streaming source. In a production environment, this might be Kafka, Event Hubs, or a directory where new files arrive. But in this demo, we're going to be grabbing files from our video streaming data directory. So let's go ahead and run this. Next step in our streaming ETL is to apply transformations to prepare the data. Here, we're parsing out the timestamp string in the proper timestamp type and extracting components like date, hours, and minutes for further analysis. So let's go ahead and run this. Next, real-time analytics often involve windowed calculations. Here, we're going to be using a 1-minute tumbling window to track streaming events by device types. We also have a watermark, which helps us manage late arriving data and state cleanup. So let's go ahead and run this. All right. And now in the next cell, we're also going to be tracking errors in real time, which is a critical monitoring capability. And this query groups errors by type within a 1-minute window. All right. Now we've done all our prep work to get the streaming pipeline going. Let's move on to the next cell where we're actually going to run this streaming pipeline. You notice that we've saved this to memory, and we can access these streaming events later by checking out the tables that this is going to create. And these tables are streaming device metrics as well as streaming errors. So let's go ahead and run this. All right. Now the streaming process has begun. This query is going to keep on going. Now, if you scroll down here, you see that it's initializing the streaming process. And you can see now we have the 2 streaming tables that is expecting data from. That's streaming errors, as well as streaming devices. So if you open this up, you get to see a dashboard as well as a raw data tab, which shows you information about how data is coming into this pipeline, as well as the data that's actually coming in, which will show in the raw data section. In the next cell, you see here that I have some monitoring checks that we can do to check on the status of this pipeline. So let's go ahead and run this. Right now, we don't see much going on because data isn't currently being passed through this, but we're going to do that shortly. In the next cell, I have a much more detailed metric that gives us even more details on this pipeline. So let's go ahead and run this. And as expected, we don't see too much going on here because no data is being passed at the moment. So to change that, I'm going to go ahead and head over to my data generation script that I have over here. So let me go ahead and do that. So in this script, I'm going to be generating some data such that we can get the streaming pipeline going. All right, let me go ahead and run this. This is generating 50 streaming events, and we've done 10 so far, 30. And as this continues, we can head back into our streaming pipeline to see how this data is coming in. All right, you can see that the monitoring graph has picked up, meaning data is coming in. Now let's go ahead and check some of the monitoring queries I have over here. You can see some rows are being added. This has 12 rows, 38 rows, and that makes sense because that adds up to the 50 records that we just generated. Moving on to the next cell, let's go ahead and run this. We can now see we have the input rate data as well as the processing rate data of the set of data that we just processed through the streaming pipeline. So with this type of data can be exported for specialized monitoring tools like Databricks Dashboard, which is in the same platform, or other tools like Grafana or Datadog. All of this are a great way for you to create dashboards and have long-term trend analysis on your ETL pipelines. And that brings us to the end of this module and also the end of this course.